Okay, so since I'm away this afternoon for part of the Block D class, I'm going to try to record this lesson, and that way everybody is able to see it, even the people who did get to see my lesson. So today we're going to talk about polynomial equation word problems. We spent the last few days talking about various polynomial equations and finding roots and finding zeros. And so now we're going to use what we know to try to solve some word problems. So our first word problem here, Mr. Davidson's family are very competitive with board games. They keep score using a complicated system that incorporates positive and negative scores. Mr. Davidson's scores last time he played could be modeled by the function s of x equals x times x minus 4 times x minus 6, where x is less than 10 and x is an element of the whole numbers, where x represents the game number. And so just like the real number system, and I believe earlier in the year we looked at the z, which represents the integers, so all the whole numbers that are positive and negative. The w just represents the whole numbers, so like 0 and then all our positive integers, so 0, 1, 2, 3, and so on. So it does not include any negative numbers at all. And part A, after which game was Mr. Davidson's score equal to 0? So if we're trying to figure out when is the score equal to 0, we want to know when is s of x equal to 0. And so we can set our equation for s of x equal to 0 and solve. And so because it's already in a nice factored form, we have that factored form equal to 0. We can easily see, well, our x has to equal 0, 4, or 6. Well, all those numbers are less than 10. All those numbers are whole numbers. So we can say, well, Mr. Davidson's score is equal to 0 after game 0, game 4, and game 6, or 0, 4, and 6 games. And this one kind of makes sense. Yeah, if you haven't played any games, I guess with this scoring system, you're going to start with a score of 0. That kind of checks out for what we would imagine. Part B, after which game was Mr. Davidson's score -5? So we can start off the same way. Our s of x this time is equal to -5. So if we sub that in, well, we have this factored form is equal to -5. Now it's really easy to solve a factored form when it's equal to 0, but when it's equal to -5, it's not quite so simple. So we're going to look to expand the right side first, move everything to one side, and then we can look at trying to factor. So I expanded out the first two brackets first, and then expanded everything, moved everything over to one side. And so at this point, I can't do any grouping. There's no common factors, anything to take out. So we can look to use that factor theorem in order to simplify this further. We only are able to use the factors of 5 divided by the factors of 1. So really only plus or minus 1 or plus or minus 5 are options. 1 and -1 don't work. When we sub in 5 as a 0, that works. So I did synthetic division with 5 as our 0 and got left with x minus 5 and x squared minus 5x minus 1. Now x squared minus 5x minus 1, that's not going to factor at all. There's nothing that's going to give us -1. Sorry, no factors are going to multiply to give us -1 and add up to -5. So this isn't something that could be factored. You could try using quadratic formula, and yeah, that's going to solve this equation, whether it's real roots or imaginary roots. But we can look back and remember, well, we only care about x values that are in the set of whole numbers. And so right away, if we're using quadratic formula, we're not going to get an answer that's going to give us a whole number. So we can just look at our first bracket here. We're only going to get an answer of x equals 5 because we had no whole number roots from this equation. And so we can answer this part B by saying Mr. Davidson will have a score of -5 after 5 games. So it looks like, yeah, game 4, I'm going to have a score of 0, game 6 of 0, and game 5, I don't know what happened. I'm in the negatives here. Part C, after which game was Mr. Davidson's score 16? Well, very similar question to the one above. And so because it is so similar, well, we already did this expansion up here. We expanded this out. We got x cubed minus 10x plus 24x. That 16 comes over, becomes a -16. And so we have another cubic equation that we can try to solve. There's no grouping available to us here. I don't see any patterns that allow 1 or -1 to work. So we're going to have to look at those factors of 16 in order to try to see if anything works out nicely there. Turns out if we try subbing in 2 as a 0, that's going to equal 0. So I've set up the synthetic division here. And once we factor that, we get an x minus 2, because again, that factor needs 2 as a 0, and our x squared minus 8x plus 8 coming from our synthetic division. Here we have a factor that's easy to see as 0. Here, we again want to see if we can factor. No numbers are going to multiply to 8 and add up to -8. So this is not going to factor nicely either. You'd have to use quadratic formula, which again means it's not going to have a whole number root. So there's no root from here that we're going to be interested in. And so because we only have that 0 of x equals 2, or that solution of x equals 2, I suppose, we can say, therefore, I'm going to have a score of 16 after 2 games. And we can start to look at, well, our part D, draw a sketch of the graph S of x if x is an element of all real numbers. So let's start to look at what information we have here. So I've set up a scale here. We know at the very least we want to talk about games up to 6. Everything was between kind of 0 and 6, so I've gone a little bit past 0 to the left and a little bit past 6 to the right just to make sure everything fits on. And then the scores that we have so far, we had a high score of 16 and a low score of -5. And so this scale should track all of our S of x as our scores on here as well. We can start plotting the points that we know. So I've plotted from part A. We knew that I'd have a score of 0 after 0 games, 4 games, and 6 games. Part B, we know that after 5 games, I'll have a score of -5. And we know from part C, after 2 games, I'm going to have a score of 16. So I've done the best with the sketch and the scale that we have to kind of graph that point here. Now, graphing polynomials. I found something in this interval. I found something in this interval. I need to check my outside intervals as well. And then I'll have checked all 4 intervals around my 3 zeros. So subbing in a point to the left, so maybe -1, into our S of x, we get -35. Well, that's going to be way off the graph here. And then subbing in S of 7, we get 21. Yeah, it's off the graph. You could put an arrow, or I did a rough idea of where it was on here. And so now we can try to connect our curve together. And so here, yeah, we're going way off the graph. Yes, I could draw an arrow kind of around this area, or here I've connected it to that point I had put on my graph, and we get a shape that looks roughly like that. And that fits all the criteria of the stuff that we've found, either from the questions up there or from some extra intervals here. So this question overall, not a very tough word problem. There's not really a lot of thinking to be done. So we'll look at one on the back here that maybe is a little bit less obvious. So an open-topped box. So a box, it's going to have its, 4 sides and a base, but no top at all. Can be made from a sheet of aluminum measuring 50 centimeters by 30 centimeters by cutting congruent squares, so squares that are all equal to each other, from the 4 corners and folding the sides up. Write a polynomial function to represent the volume of such a box. Determine the side lengths of the squares to be cut out and removed to create a box with a with a volume of 4,000 centimeters cubed. So the very first thing I'm gonna draw is our sheet of aluminum. So that's like a completely flat piece of aluminum, and it measures. What's going on with the focus worked? It measures 50 centimeters by 30 centimeters. So we have, a rectangular sheet, 50 centimeters by 30 centimeters. So we want to cut congruent, so that means, again, they're all the same. All the squares are the same. Cut congruent squares from the 4 corners. So 1, 2, 3, 4 squares in the 4 different corners. And that would let us, I don't know how well this is going to translate, but that would let us fold kind of along here in order to bring this side up. And we would fold right here to bring this side up. And so we would have these 4 little tabs fold up. So maybe this helps visualize it a little bit better. But yeah, these shaded in parts, they're getting cut out and just like fully removed. So this does not exist anymore. And now the blue rectangles like our base of our box, and all these little pieces are going to get folded up and folded up. And that's going to create the bottom of the box with 1, 2, 3, 4 sides folded up around that. So yeah, when these get folded up, these sides here, that side and that side there, they're going to touch because they'll get folded up and make like a 3-dimensional shape. So it's going to be a bottom and 4 sides with no top. Now, I don't know if you remember in elementary school, like I had to do this. I don't know if you had to do this, but we would make like maybe cubes out of a shape that looked like this. And so yeah, you like kind of cut this out and folded it, and then it would give you a cube with like 6 different sides. You have the 4 here that would kind of go all the way around, and then maybe a top and a bottom. So this is very similar, except you have 1, 2, 3, 4, 5 sides. It's not quite cubic because they're not squares. And so we have 5 sides. We're not going to have a top. Same idea. I don't know if this helps at all to visualize, but if you ever did have to fold a shape that looked kind of like that, I think they called it maybe a mat in elementary school, like a mat of a cube. I could just be making that up. But that's what this shape looks like. Maybe if you look at the front of the room, if you're in class right now, I may have a lined piece of paper with some corners cut out that I used to try to explain this to the other class who did get to listen to my lesson. So the question itself asks us to find the side lengths of these squares that are being cut out and removed. So we can say that the side length of these squares, so it doesn't matter which square you pick, they're all the same, but we're going to say x is the side length of the squares that were cut out. And so since this whole big sheet was 50 centimeters long, and I've cut out an X here, and I've cut out an X here, this blue base, its length is going to be 50 minus those 2x's we cut out. So we can say this whole side here is 50 minus 2x. And similarly, the length, I don't know if I just said width or length, but the other side of this base is going to be this 30 centimeters minus the x that we cut out here and minus the x that we cut out here. Because these sides are like the flaps that get folded up. So they're not going to be they're going to be part of the height of the box, not the length or the width. And so this is all looking at like that flat sheet that we're cutting out and about to fold up. After we fold up those four sides, we're going to get something that looks like this. So you have your length and width of that box, and then the sides that got folded up, they had a height of x. They had a height that matched like how much did we cut out of these squares. And so we're going to get an open box, open topped box that looks something like this. Now we know we want the volume of that box to be 4,000 centimeters. Oh, let's focus. 4,000 centimeters cubed. And we also know the volume of a box of really it's like a rectangular prism is your length times your width times your height. So our length, our width, and our height, doesn't really matter what you call length and width. One of them has to be length, one of them has to be a width. Doesn't matter the order we multiply things in, but these three terms multiplied together needs to equal 4,000. Just like we did on the other side, we're going to expand this out and move everything over to one side so that we have an equation equal to 0. And so again, I broke it up, multiply these two terms together, and then as I multiplied by x, I reordered things so that we went from highest degree to lowest. And that 4,000 came over to this side and became negative 4,000. Now before we do anything, there's a common factor here, so let's take that out. So we take our common factor of 4 out, and we get left with x cubed minus 40x squared plus 375x minus 1,000. No grouping's going to work. We have to look towards our factor theorem here. And so you have a lot of options. We have all the factors of plus or minus 1,000 to check. Hopefully we get something to work fairly quickly. So plus or minus 1 don't work, plus or minus 2 doesn't work, plus or minus 4 doesn't work, and finally if we check 5, 5 is a 0. So that's telling us like x minus 5 is a factor. So we can do our synthetic division. We do our synthetic division, we get some pretty big numbers, but it still works. X minus 5 was our factor, and we get left with x squared minus 35x plus 200. And we don't have a way to multiply numbers to 200, add up to negative 35. So this isn't going to factor. We should look at our quadratic formula and see what answers that gives us. So if we go through with our quadratic formula, eventually we get 425 in our square root, and we can split that into a square root of 25 and a square root of 17. Take our square root of 25, we get 5. And this is as far as we can go simplifying that root, I guess, our quadratic formula roots. So we get this answer here, and we can ask ourselves, like, does this make any sense for this problem? And so investigating a little bit closer, if we use the positive square root, we get an answer of 27.8 centimeters approximately. And if we use the negative square root, we get approximately 7.2 centimeters. And so very common, our first inclination might be, well, those answers are both positive numbers. That sounds pretty good. We're talking about like a length, and they're both positive. Usually we just don't care if we have a negative length. But if we look at our original problem, we had a 50 centimeter sheet and a 30 centimeter sheet, and I had to cut in X both directions. Well, if my X is 27.8 or almost 28 centimeters, that would mean I'd have to cut 28 centimeters this way and 28 centimeters this way. And that's not possible if I only have 30 centimeters long to cut through. Same with the 50. I can't go about 28 centimeters in both directions. There's just not enough aluminum sheet there. So we would say that this answer here is inadmissible, which means it solved the equation mathematically, but it doesn't really make sense for this problem. So yes, this answer doesn't make sense. It's inadmissible. And we can even go a step further. From our original problem, well, the most I could cut out is, like, I could go 15 this way and 15 this way, and then, well, then I'd have no base left over. So yeah, 15, really we don't want to include 15, so I put a round bracket, but that's the highest our X can go. And the lowest our X can go is 0, because, yeah, we can't have a negative length, a negative amount cut out. But if I don't cut out anything, I don't get a 3D shape. So this we can say is what are our restrictions on our domain. I've written it in that interval notation we talked about one of the first days of this class, but I put round brackets because we don't really want to include 0, because then it's not three-dimensional. And we don't really want to include 15 because it's not three-dimensional, but our X is in that interval from 0 to 15. Not exclusive. Not inclusive, I guess I should say. 7.2 centimeters, we talked about that. That sounds reasonable. I can go 7 centimeters this way, and yeah, I'd have a reasonable base left over. And so then we can look to talk about our final answers here. And so we had this X equals 5, and one of our two answers from our quadratic formula made sense for the problem. So we can say, therefore, those square cutouts, they should either have a side length of 5 centimeters, or, well, that 7.2 is our 35 minus 5 root 17 over 2. And so this is our exact form. And they never really mentioned anything about rounding up here. I know a lot of the times our word problems, that's what we're used to doing. But if it doesn't mention rounding, it is completely acceptable. And in the end, if you keep going forward with math, it's preferred if you write it in this format, because this is the exact number. 7.2 was rounded. This is exactly what that side length would be in order to give us one of our answers where the volume is equal to 4,000. So may look weird. It's okay to write your answers in this exact form. In fact, it's going to be preferred going forward in a lot of your classes, especially if you keep doing sciences. Maybe not sciences, but math specifically in university. If you round that answer, I'm okay with that. Show your work, but don't make extra work for yourself if you don't need it. You don't need to find out that exact answer. It's okay to write. You don't need to find out that approximate answer. It's okay to write your exact answer. So that's the end of this example as well. You'll notice there is one exactly like this in the practice. Let me know if you have any questions on anything at all. I will be in my portable tomorrow at lunch and Friday at lunch. And so if you have any questions that you don't want to try to email me, come in, let me know how I can help, and I'll see you tomorrow. Bye.